Welcome to week 4. This week we are in biology and the brain, and we are doing scans and systems. So, a quick week for us this week, but we have a lot to get to, so let's get going. So the central nervous system, which we kind of talked about last week when we talk about neurons and how they fire, the central nervous system is in charge of all of your nervous system. It is your spinal cord, it is your brain, it is the functioning and the processing of all of your neurons. Now the spinal cord is a long bundle of neurons that carries the messages from your peripheral nervous system to your brain. Remember, your brain is in charge of everything in your body, and the spinal cord is the one that brings all the messages from your peripheral and everything non-central nervous system and brings it to your brain. And it's responsible for the very fast and life-saving reflexes we have that are hardwired to it. Now, the reflex arc, which is the biggest component of the spinal cord, is the sensory neurons, motor neurons, and interneurons are all located and used here. Now, sensory neurons are in your peripheral nervous system, and they're carrying that information from your senses all the way to the central nervous system. Your motor neurons are neurons carried from the central nervous system to your peripheral nervous system with that information, and the interneurons are located in the spinal cord and in your brain, and they're the ones that are processing all this information. So they're going to be the ones making up the most of your brain. Now, the reflex arc is based on neuroplasticity, is that your body responds to things very, very quickly. It also is able to change and adapt and function in different ways. Now, when you think of the spinal cord reflexes, what you need to think of is a basic thing, like, for instance, flame in your flame touching your fingers. What happens is your sensory neurons pick up that fire is touching your fingers. It goes all the way up to your sensory neurons, excite the interneurons at your spinal cord, and say, "Oh my God, this is happening. There's something wrong." Then all of a sudden, your interneurons excite the neurons, the motor neurons in your spinal cord, and it sends the motor neurons back and pulls you forward. So the message never gets to your brain. Your brain does not process this information. It's just like if you had no idea and I blindfolded you and put your finger over a fire, you'd flinch before you even knew that your finger was really that hot. I mean, before you could process, "Oh my God, my finger's hot," your body would have already responded. Because you don't have time to think means your body reacts quickly. That is the reflex. Now, your peripheral nervous system is everything not central nervous system, and it's all nerves and neurons that that are not contained in the brain and spinal cord, but are throughout the body themselves. And it's broken up into two major sections: the somatic and the autonomic. Now, the somatic are all your voluntary movements, like moving your hands up and down, doing the YMCA, and doing all that. While your autonomic or automatic is everything that you do not control yourself. Now, this is what your peripheral nervous system looks like. Of course, your brain and your spinal cord are not a part of the peripheral nervous system. Those are your central nervous system. But as you can see, all the receptors throughout your whole body and all the connection points, that is your peripheral nervous system. Now, the first major part of the somatic nervous system stands for body. Now, the somatic nervous system is a division of the peripheral nervous system that carries information from the senses to the central nervous system. So it's all of those that are pulling out the information. Now, this is dealing with voluntary muscles. Somatic is body, somatic, voluntary. Now, the sensory pathway nerves come from the sensory organs consisting of sensory neurons. So, sensory passageways are when sensory neurons are firing and the route they travel. Sensory neurons only travel on sensory pathways, while motor neurons only travel on motor pathways. There are two different lines to keep everything clear and high functioning. Because think about it, when you're injured, it's not just one thing that is hurting, there's many different things. Now, obviously, if I step on your toe and then cut off a finger right after, you're going to notice your pain in your toe, but mostly you're going to be horrified by what happened to your finger. Your brain has to be able to process all of your sensory neurons and your motor neurons at the same time. That's why they have to keep them straight. That's why it's not one central line. Now, when we talk about the autonomic nervous system, it's within the peripheral nervous system. It's dealing with all your autonomic, everything that is involuntary. For instance, your heartbeat, your digestion, all of those different types of things. Now, in the autonomic nervous system, there's two types, the sympathetic and the parasympathetic. Now, your sympathetic is going to be your fight or flight, and it's going to be everything that gets your body able to react to stressful events. Your parasympathetic is going to be the one that restores your body to normal functioning, slows you down, calms you down, and allows you to have the epitome or the optimal creation of output from your body. So the sympathetic is going to rise that temperature. It's going to increase your body's abilities to perform, while the parasympathetic is going to allow your body to slow down and recover. Now, when you think about your parasympathetic and sympathetic, here are some examples. Now, your parasympathetic is going to increase salivation when you're thirsty. It's going to slow your heartbeat down. It's going to increase digestive functions and stomachs and all that stuff when you're full and all that stuff. Your sympathetic, it gets your body ready to go, is going to increase your heart rate, decrease salivation because it's going to need to retain that water. It's going to decrease digestive functions, all of those different types of things in order to allow your body to function as highly as possible. Now, here's some visuals for you. As you can see, it's broken down. Now, we did do this on Friday on your focus as the first day of the week. As you can see, the autonomic is going to be broken down into parasympathetic and sympathetic. So make sure you understand the flow chart. Peripheral system has autonomic and somatic. From the autonomic, you have parasympathetic and sympathetic. And sympathetic gets us excited. Now, the other component of this week is brain studies and how we look at the brain in different ways. Now, one of the ways we study the brain is called clinical studies, and that is when we look at specific people and how their brain function has changed when parts of the brain is experiencing or has been damaged. For instance, one of the ways doctors have done this is deep lesioning, which is when we insert a little wire into the brain and where we destroy parts of brain cells for the wire. We do this in areas, in extreme cases, but narcolepsy has been treated this way, where we stop that part of the brain from kind of functioning. It allows us to kill off a little part of the brain as specifically as we can in order to achieve some sort of end. Now, we also do electrical stimulation of the brain, which sends a mild electric current into the neurons to see how they react. This is like baby steps to what we'll be seeing later with electrical, when we start electrocuting brains to kill them. We're just trying to stimulate those brain cells, thinking that maybe they haven't been essentially studied before or stimulated before. Then we have human brain damage. What happens is that when people have experienced terrible things, like Phineas Gage, who we'll be talking about this week, when we talk about Phineas Gage, what we're looking at is how did he react? How did his brain change with the railroad spike going through his head? Now, other ways we do it, which are still a little shocking, is your EEG, which is considered to record the brain activity waves. When we're studying sleep patterns, all those different types of things, this is going to be recording all that brain behavior. When they talk about how men and women see chocolate differently, women are way more, our brains light up like crazy. That's what we're looking at is EEGs, seeing how fast our brain increases. Now, other major studies of the brain are going to be your computed tomography, or the CT, which is using controlled x-rays of the brain. It is looking at the brain in different, essentially slices. Your MRIs are brain imaging. They're going to give you the most detail of the brain is an MRI. And that's why MRIs are so popular, because they are going to give us the most detail. We also have functional MRIs, which kind of makes a movie out of your MRIs, and it allows us to see brain activity from different time periods. So instead of just seeing one set image, we're allowed to look at how the brain has changed in its activity by viewing the MRI at different times and seeing how they come together. A PET scan is when we have someone ingest a a really disgusting chemical, which I can't think of the name of it at the moment. And what it does is it lights up your brain, a radioactive concoction. It's like this really chalky, terrible, disgusting thing. Anyway, you drink it about half an hour before you go in. And what it does is it tells you what part of your brain is being activated during that. So we can see what part of the brain is activated when you see your mom, when you see your dog, when you feel anger. It allows us to see what is happening in what part of the brain. Well, guys, that is the this week. As you can see, it's short and sweet, which thank goodness for this week. I hope you're doing great, and please let me know if you have any questions. Good luck, guys.